So yesterday we went over the definite integral as when we're given a graph. Okay, so how do we find the definite integral of a function if we have a graph of that function? In other words, what does the definite integral have to do with the graph of the function? Okay, your notes from yesterday, please. Number. Oh, what does it have to do with the graph? If you're given a graph, how do you find the definite integral? Over a line. The area of the. So it's the area, right? So we get this. So the definite integral is the area bounded by the curve, the x-axis, and your bounds, right? So it's that area, right? How does the derivative relate to the function, by the way? You have a function and you have a graph. How does the derivative of that function relate to the graph of that function? What does the derivative tell us? What is the, no, think about it, just, guys, think. Derivative, what does it tell us about the graph? What is the derivative? Say again? It tells us the slope of the graph. Okay, so the derivative tells us the slope. The integral tells us the area below the curve. Okay, so can we find the integral at a point? What do you think? So think about that for a second. If you found the integral at a point, would you have any area at a point? No. Okay, so there's no such thing as an integral at a point, unlike the derivative. You can find the slope at a point. There's no such thing as integral at a point, really. Okay, so here we're going to be looking for, again, definite integrals. And this time, though, we're given an equation, or not an equation, I'm sorry, an expression. We're going to evaluate the definite integral from -2 to 5 of absolute value of x. So let's do that by graphing the function and summing the area. So if we're not given a graph, we can graph the function. So let's graph the absolute value of x. Now our lower bound for this integral is what x value? Okay, so -2, and the upper bound would be 5. So on my x-axis, all I'm really concerned with is from -2 up to 5, at least for now. And so we're going to essentially substitute in our values. So we plug in -2 to the absolute value of x, we get 2. So I'm going to have a y value at 2. And if we substitute in 5, we get the absolute value of 5, which is 5. Okay. Now, is this going to be a straight line? Straight across? Is that what the absolute value of x looks like? No. If you're not sure what a graph looks like, you can always revert back to just plotting some points, right? So like when x is 0, what's the y value? 0. Right? Now we should know what the absolute value of x looks like. It's what shape? A v. And the v, the crook right there, the cusp, is at what x value? 0. So we should just have a v. And we're integrating from -2 to 5. So we're bounded by that line and by that line. And so what shapes do we have here? We've got 2 triangles. So we're going to find the area of this triangle and the area of this triangle. Since they're both above the x-axis, are we going to do any subtraction here? Okay, so since they're both above, they're both positive, so we'll just add them together. So the integral from -2 to 5 of the absolute value of x dx is equal to, okay, now we got 1/2 is remember our formula, 1/2 base times height. So 1/2, the base of the first triangle is 2, the height is 2, plus 1/2 5 times 5. So here's a little trick, and it dawned on me about halfway through third period that's useful. So if you guys wrote this, what would you write? 2, right? And then if you do this, what do you get? You get like 25 over 2, right? So you're going to add 2 and 25 over 2, but so then you have to get back to a common denominator and stuff like that. So why not just leave this as 4 over 2 plus 25 over 2? All right? That way we don't have to go back to 4 halves. So 4 over 2 plus 25 over 2 gives us 29 over 2. All right, so since the denominator is going to be a half, anyway, we might as well just leave it there so we can just add 4 and 25. Okay. Grab your calculators really quick. I didn't show third period here, so maybe we'll watch the video again. Okay. Now remember, we're doing integrals here, right? So how do we get to the integral feature on the calculator? Okay, you go menu, calculus, integral, or what's the 2-button shortcut? Shift plus, right? So if we press Shift plus, we can integrate. And now we actually have upper and lower bounds. We can fill in those values that are showing the little empty squares. We can put -2 and 5 into those values, into those little empty squares. Okay, so we can go Shift plus. Now we're going from -2 to 5. The easiest way to get around again is tab. Use tab to jump around. And then control tab goes back. Or no, shift tab goes back. So tab is forward, shift tab is back. And so we want the absolute value, so we get that under our catalog button right here. Absolute value of x. X. And so we get, oh, help with this negative. -2. There we go. So we get 29/2. Okay? So you can check your answers. Once we have a function here, I think this came up yesterday. Well, are we ever going to be given a function? Well, yeah. Okay. Well, sometimes you're given a graph, and other times you may be given a function. Once you're given a function, you can actually, the calculator will integrate it, no problem. But these kind of problems, more likely than not, will be on a non-calculator portion, because they're checking your ability to integrate, not the calculator's ability to integrate. And I'm checking that. So example 2 says, same thing, compute the value of the integral from -1 to 5 of f of x dx by graphing the function and summing the areas. This time we've got a piecewise function. You know how much you guys love piecewise functions. So let's graph. Now our bounds here are from -1 to 5, right? So we're definitely going to have -1 on our x-axis and 5 on our x-axis. And then what's the other important value here that we're going to be looking at? We're looking at 0, where it changes. Okay? So wherever your function changes, that's the important value you're going to be looking at. So we plug in our n value to whichever function is appropriate, so our lower bound. Plug in where it stops, essentially. Right? Draw that function. Then plug this into the second function, and then the end bound, 5 in this case. Okay, so when we plug -1 into f of x, first off, which one's going to apply when x is -1? Okay, so this one will. So we plug in -1, we get -1, so we get +1. So when x is -1, y is +1. Okay. What's the next value we want to plug into the top function? I want to plug 0 in, because that's going to be where the function stops. We plug in 0, well, that's at the origin. Now, what does y equals -x look like? Is it a curve or a straight line? Straight line. So we can just draw a nice straight line. Okay. Then we plug in 0 to the second function here. And what do we get when we plug in 0 to the second function? 2. So we got point at 0, 2. And then we're going to plug in our highest, our upper limit, which is 5. -5 plus 2 gives us -3. So we're down here at -3. Now, what does the graph of -x plus 2 look like? A straight line connecting these 2 points for sure. So draw a straight line. Okay, so we've got a triangle. Can we find the area of a triangle? Okay, so we've got this triangle here. Then we've got this triangle here. Right? We've got these 2 triangles that are above the x-axis, and then we have a triangle below the x-axis. Okay? Now, what other bit of information are we going to need here to find the area of these 2 triangles that we don't have just right now already labeled? where it crosses the x-axis, right? What's another word for where it crosses the x-axis? Someone give me another word for it. Zero, root, x-intercept, solutions. These are all things that can show up. I might say the roots, I think on the paper yesterday, there was a question that said something about the roots were at -10 and at 4.25, and that threw some people off going, why are you telling me that? Right? That's just telling you this specific value. So this specific value, well, what is that? What's going to make the y value 0? Plug in what? Okay, and what value is going to make it 0? 2. Okay, we don't really plug in. We set this equal to 0, right? Now we know it equals 0 at 0, but that's not our concern. It's also 0 when x equals 2. So this value must be 2. Okay. Now when the area is below the x-axis, what does that mean? Okay, we have a negative integral, so we subtract from the rest of it. So our integral from -1 to 5 of f of x dx, and yes, you need to write this notation. Okay, you write this notation. I noticed on the test yesterday there was a lot of some really bad notation, and sometimes you're losing track of what you're doing. From here on out, where we're doing integration, it's really easy to lose track of what you're doing if you don't have notation written down. So you really want to keep track of it. So we have the integral from -1 to 5 of f of x dx. So we've got one triangle. So that's 1/2. Has a base of 1 and a height of 1. So 1 times 1. Plus another triangle with a base of 2 and a height of 2. So 1/2, 2 times 2. And then we've got an area below the x-axis, so we'll have minus 1/2. And this base is 3, the height is 3. So 3 times 3. So we've got 1/2 plus 4/2 minus 9/2. So 1 plus 4 is 5. 5 minus 9 is -4. -4 over 2. So we get -2. Now the fact that this came out negative, what does that tell us about this graph? Or about, I guess, about the areas of not the graph. The definite integral is negative, that's for sure. But what does it tell us about the areas? The fact that it came out negative. So there's more area below the x-axis than there is above the x-axis for this particular function on this particular number. Okay? And that's going to be relevant when we actually apply this, when we see how this is applied. Okay? Same idea, compute the value of the integral from -2 to 5 of -x plus 3 by graphing the function and summing areas. What are the x values we're concerned with? Okay, so -2 and 5. Now, since this isn't a piecewise function, but what kind of function is it? Linear, we know it's just going to be connecting two dots. So which two values do we want to plug in? We want to plug in our endpoints, -2 and 5. So we plug in -2, -2 is +2 plus 3, so -2, 5. And we plug in 5, well, -5 plus 3 is -2, so 5, -2. And so we've got a nice straight line. And so we're going to break this up into what shapes? And how many triangles? Two. And how are these triangles different? Besides their size, of course. Okay, so one is above the x-axis and one is below. So this integral will be positive and this will be negative. So when we find the integral from -2 to 5, if our graph has any scale whatsoever correct, should our answer be positive or negative? Okay. If my scale has any correctness whatsoever, it better be positive because this area right here is much bigger than this area right here. Now, keeping in mind my scale may be completely wrong, I'm going to have an open mind about it, right? In other words, this is -2, this is 5. If it's not to scale, then all bets are off. But so what other value are we going to need here? Okay, the 0 or the root. So how do we find that root? Okay, we set this guy equal to 0, and that's 0 at 3. Okay. So the integral from -2 to 5 of -x plus 3 dx will be 1/2 times, and this triangle has a base of 5 and a height of 5, minus 1/2 times, and this has a base of 2 and a height of 2. So we've got 25 over 2 minus 4 over 2, which equals 21/2. And was our answer positive? Does that fit with what we were kind of expecting? Okay. All right. One more example. So up until now, everything's been linear, right? Is this linear? Can we share the square root? Just break this up into two separate, nice and easy and linear? No, right? Okay, so lesson learned. Can't share it. So what kind of a function is this? What is this a graph of? Or what is the graph of this function going to be? Think back to where we've seen anything like this before. We have. So the general equation for this kind of a function is y equals the square root of r squared minus x squared. That's a semicircle with a radius of r. And this, if it's a general form, it's centered at the origin. Okay, so this is the general form for a semicircle with radius of r centered at the origin. Okay, so what is the radius of our semicircle? Okay, so we look at this as r squared, right? So that means r must be 2. Now this, the minus 2, this is a horizontal shift. Inside the parentheses, inside the square root, so it's a horizontal shift. And remember, when it's inside, it's horizontal, and it's backward. It's the reverse of what it seems like it ought to be. So minus 2 seems like it ought to be going to the left, but when it's inside, it's reverse. It means it's going to the right 2 units. Okay, if there was something after it, like plus 4, it would be up 4 units. Okay, so outside is up and down, inside is left and right. Okay. So this semicircle has a radius of, so r equals 2, the radius of 2, and it's centered not at 0, 0, but at 2, 0. So let's draw the semicircle. Okay. Now again, it's centered at 2, 0, and it has a radius of 2. So how far to the left is our semicircle going to go? At the origin, at 0. And how far to the right is it going to go? All the way over here to 4. So here's 2, 4. How far up is it going to go? 1, 2. What are we integrating from and to? From what to what? From 0 to 4, which is awfully convenient considering that's our semicircle in its entirety. So we're finding the area of that semicircle. So the integral from 0 to 4 of the square root of 4 minus x minus 2 squared dx is equal to, now how do we find the area of a semicircle? Half pi, and then what's the radius here? So half pi 2 squared, which gives us an integral of so let's just confirm that using the calculator, because I don't know, 2 pi seems like such an interesting answer for this kind of a problem with no seemingly trig stuff in it at all, and suddenly pi is showing up, right? So we have the integral, so shift plus from 0 to 4 of the square root of 4 minus, 4 minus x minus 2 squared dx. There we go. So that's pretty much it. Graphing a function, finding the area bounded by the function, the x-axis, and then the vertical lines that are the bounds. Did you have a question? Any concerns or problems right now? So there's 9 problems, if I'm not mistaken. They are a little time consuming just because of the graphing process, but it's really important you guys practice this graphing stuff by hand. It's probably been a little while since you've really graphed stuff by hand, at least since last semester. And so you want to practice that now.